Okay, so today we discuss this first and then we will go up to joint characteristic functions. Okay. We are given jointly random variable. Okay. Then we define the moment MKR as where Pxy is the probability density of joint probability density of xy, okay, x to the power k, y to the power r, and this will be called joint moment of xy of order n is equal to k plus r. So, it is very much similar to the moment that we dealt with for a single random variable case. It is a generalization of that to two variables. Okay. Certain things follow easily. What is M10? That means x to the power 1, that is x, y to the power 0, that is 1, x, p x comma y dx dy. And p x comma y can be written as, that is p x comma y can be written as you can write the entire thing like this, x p x dx, p x comma y will be written like that is p x comma y is p x times p of y given x. So, this integral is 1 because condition to any x, total probability of y taking values within minus infinity infinity, that is equal to 1, and this is the mean value of x. So, M10 is mu x. Similarly, M01 will be mu y. Mu y means the mean of y. Okay. Then what is M11? Or say start with M20. Clearly it will be expected value of x square. Why? Y0 is 1, x square, p x comma y dx dy, p x comma y will be written as before like p of y by x and then p x, this integral will be 1 and we get expected value of x square. Similarly, M02 is e of y square and M11 that is expected value of xy. Okay, that is, these are all second order moments. Okay, second order joint moments. Similarly, you can have joint central moments. Here you can call it M prime KR. It is actually expected value of, so earlier it was x, now it is not x but x minus its mean mu x raised to the power k, y minus its mean mu y raised to the power r, or equivalently okay. So you can easily see what is m prime 1 comma 0, y minus mu y to the power 0 is 1, x minus mu x, p x comma y, that we again as before write as before, p x and p y by x, p y by x integrated with respect to y from minus infinity it will be 1, because okay, and this integral will be x minus mu x times p of x. Since mid of x is mu x, that will be 0. So this will be equal to 0. Similarly, also will be 0. Okay. How about m prime, or just a minute. How about 2 0? That is nothing but expected value of x minus mu x whole square. So that is the variance sigma x square, and m prime 0 2 is by the same reasoning sigma y square, and m prime 1 1 will be what? Expected value of x minus mu x times y minus mu y, which is nothing but the covariance, right? So that is equal to c. Okay, we will take up some example, but before that, I mean, we come back to some topic which I had left out, but I need the results from that topic for subsequent treatment here in the context of moments and characteristic functions. So I come to that topic first. That is, earlier we had considered joint random variables, say x and y, and a function, a single function of these random variables, that is maybe z is equal to f of x comma y. Okay. But now we will be considering two such functions, one is z and another is w, two different functions, but both are functions of joint functions of x and y. So both z and w will be random variables. So we are considering two functions of two random variables. Okay. That is, we are given and w is equal to g of x comma y. Okay. Obviously, z and w, since they are functions of x and y, in general they are also jointly random. Okay. So I can have joint probability distribution and joint probability density functions for w and z. So I am suppose interested in finding out if that is the joint distribution of zw, that is probability of z less than equal to capital Z, w less than equal to capital W, total probability. This is a joint probability distribution. We have to evaluate this in terms of the given joint density of x and y, okay, or given joint probability distribution of x and y. Okay. So this set we consider sorry. So, this covers, this actually describes an area in the ZW plane where for any point z comma w we have z less than equal to capital Z, w less than equal to capital W. This is equivalent, this corresponds to some area d ZW in xy plane. That is, it means that for any x comma y belonging to this area dZW, the corresponding small z and small w, they satisfy this relation, which means the probability of z and w simultaneously satisfying these inequalities is same as the joint probability of x and y falling within or remaining within this area dZW in the xy plane. Okay. That is, that is okay. Now, let us take an example. Suppose it is given that z is equal to positive square root of this and w is, as an example, y by x. So, we have got one function z, a function of x y, and another function, another variable w, which is a function of x y again, but two different functions, right. What does this corresponds to? That is, here if small z is less than or equal to some capital Z, this amounts to a circle, okay, of radius capital Z. So, the whole area inside the circle corresponds to Z remaining less than or equal to capital Z. Okay. That is very obvious. But how about this? This means y is equal to Wx. For our example, suppose W is positive, just because W can be positive or negative, but just for our example, suppose W is positive. That means we just draw a straight line okay, y equal to Wx. So, that means W capital Wx, that means W less than equal to capital W means what? First consider this side, when x is positive and small w is less than equal to capital W, then y is any point below this line, because on this line y is capital W times x, but for any small w less than equal to capital W, say less than capital W, the corresponding Wx, okay, will be below this. Okay. So, that means for positive x, any y here below this line will give rise to a ratio y by x equal to small w, that is less than capital W. If we include this line also in this area, then it will be less than equal to. So, we have got this area for positive x. I am taking the overlap between this circle, okay, because the circle corresponds to this inequality small z less than equal to capital Z, and the whole region below this straight line was giving rise to small w less than equal to capital W, but I am only taking the overlap between the two, the circle and that region. So, this shaded region comes. Now, we go to the negative x. If x is negative, then Wx also is negative, because Wi, for example's sake, I took W to be positive. So, Wx also is negative. So, minus of y or any on this straight line, I mean minus of some negative y divided by negative x, still the ratio is positive, you get W. Okay. But if you go up, then even if y is negative, its magnitude is less than earlier, and x remains same, negative but same, which means the value of the ratio becomes less. And if you go to this quadrant, then I mean the second quadrant, then y has already become positive, and y by x, where x is negative, is a negative number which is less than W. So, in this case, as we go above this line, we come across points where the ratio y by x is again less than capital W. Okay. So, joint probability of z less than equal to capital Z and small w less than equal to capital W is same as the joint probability of x comma y falling in this region and falling in this region, falling in the two shaded regions. Now, up to this it is okay, but now to compute that probability, I now need the probability density function, joint probability density function for x and y. Okay. Suppose it is given that x, y, they are circularly symmetric and Gaussian or equivalently called normal, that is P of x comma y, suppose is given to be circularly symmetric, jointly Gaussian, 0 mean. Okay. In this case, first, what is the probability of x, y lying within this entire circle? We have worked out this earlier. Okay. That is when we dealt with a single function of two random variables. So, z is equal to square root of x square plus y square, and x, y are given to be circularly symmetric, jointly random variables. In that case, we found out the total probability of x and y pair falling within this circle. Okay. What is that expression? That expression is that was 1 minus e to the power minus z square by twice sigma square. Okay. That was the probability of the pair x comma y lying within a circle of radius capital Z. But now I am not interested in the entire circle, rather I am only interested in the shaded area. So, how much is the shaded area? For that, I consider this angle, call it theta, and this angle is pi by 2, right? And from symmetry, the two areas are same, obviously. If this angle is theta, this is also theta. This is 1/4 of the circle, this is also 1/4 of the circle, these two areas are same from symmetry, okay. So, whatever be the area of this shaded portion which is shaded by blue, just twice that will be this area of overlap, right. Now, what is this area? First, how much is this angle? This angle is pi by 2 plus theta. What is theta? Theta is tan inverse capital W. Okay. Obviously, theta is tan inverse capital W, because tan theta is the slope. Slope is capital W. Slope of the straight line is capital W. So, what is theta? Theta is nothing but tan inverse capital W. So, this total angle is, let me erase some portion. So, this angle is nothing but pi by 2 plus tan inverse W. Okay. Let me call it theta prime. So, theta prime is tan inverse W. This total angle I call theta. And total angle around origin is 2 pi, out of which theta here and theta here. So, twice theta. Okay. So, that means what is the probability of x comma y falling in these two shaded regions? It is nothing but twice theta, one theta from the blue shaded region, another theta from the pink shaded region. So, 2 theta divided by twice pi, that is the ratio, times 1 minus e to the power minus z square by twice sigma square. You can also put uz, because z can be 0 or positive, z can be negative, that is the radius of the circle. Okay. Why 2 theta by 2 pi? Because 1 minus e to the power minus z square by twice sigma square, that is the total probability of x y remaining within the entire circle. But I am now not interested in the entire circle, but just a segment of it. What is the proportion of that segment vis-a-vis the total area? That is nothing but twice theta by twice pi, because the two angles are theta and theta 2 theta, but total angle is 2 pi. So, the ratio is just twice theta by twice pi, or that is theta by pi. Okay. So, that is your, you can write that is equal to your FZW. Okay. So, that is an example for computing the joint probability distribution function. How about the joint probability density? That is P ZW, capital ZW. What is the physical meaning of it? In the ZW plane, there is a point capital Z, capital W. Around that there will be a small area. Okay. So, the probability of Z comma W falling in this area will be equal to this function P_ZW of Z comma W times dz dw. This is dz, this side is dw. So, dz dw. Okay. This function is then called the joint probability density, that is by as per definition. Now, as I told you, Z is a function of x comma y, f of x comma y, and W is a function of again x comma y, say g of x comma y, and therefore Z and W are jointly related, and therefore we consider the joint density. Now, what is the joint density? Given the joint probability density expression for x y, and also the two functions are of course given, that is Z equal to f of x y where f is given, W equal to g of x y where g is given, and the joint probability density of x y, that is p x y, is given. Then we have to evaluate this. Now, while the procedure remains same as before means when we had just one variable at hand, I will not go into a derivation because this derivation is little more complicated than earlier. I will only quote the result and show an application of it. Okay. Here, suppose capital Z is given and capital W is given, you solve them, you get solutions like x1 y1 x2 y2 dot 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 xn yn dot 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 dot. Okay, so for x equal to x1 and y equal to y1, so this is satisfied. F of x1 y1 is z, g of x1 y1 is w. Similarly, f of x2 y2 is z, g of x2 y2 is w, and likewise. Okay, so on and so forth. In that case, so first, what I repeat again, what we first do, you started with some known capital Z and known capital W. Okay, I first put them in this equation, solve them. Suppose I get some discrete solutions for x y, there is either x1 y1 or x2 y2 or dot 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 xn yn and so on and so forth. So these values are known, they are all available in terms of giving Z and giving W. Then what I do, the formula is this, is equal to pxy at x1 y1. Mind you, x1 and y1, they are now available in terms of capital Z and W. So this indeed actually becomes a function of Z and W. This divided by determinant of a matrix. Okay, and that matrix is called a Jacobian. So I will tell you what is a Jacobian. Then again put the second solution, divide by the corresponding Jacobian, and so on and so forth. This is the result. Where, let me give the expression for the Jacobian. You can either write it like del z, del x, del z, del y, del w, del x, del w, del y. So it can be shown that this is also the inverse of okay, this is called of the transformation which transformation, that is z equal to fxy and w equal to gxy. This transformation, it takes xy pair, gives you zw pair. So this transformation has a Jacobian, which matrix actually is defined like this. So this probability density means evaluate Pxy at one solution x1 comma y1 which is available in terms of z and w divided by the determinant of the Jacobian at that x1 and y1. So again it's a function of z and w. Then again do the same for the point x2, y2 and so on and so forth. Okay, this is a result. We will not prove it, but we will just see some example where we use this result. Suppose we consider a thing like this. That is, suppose it is given that z is equal to some ax plus by linear and w is cx plus dy, and it is given that the determinant of this matrix AD minus BC not equal to 0. So you can easily solve this, right? We can easily solve this. The solution x also will be available as a linear combination of z and w. Y will be available as a linear combination of z and w. So you can even write the solutions like okay. And how many solutions? For a given capital Z and capital W, this is a linear equation, so only one solution. No such x1, y1 and x2, y2 and x3, y3 and all that. Okay. So using our previous result, it then become obvious that is what? This is equal to, what is the Jacobian, by the way? Del z del x is A, del z del y is B, j x comma y, del z del x that is A, del z del y that is B, then del w del x C and del w del y D. So the determinant of that is AD minus BC. Okay. And we take the mod of that, by the way, not only just determinant, mod of that. I must qualify my previous statement. This after taking the determinant can be negative or positive, but take the mod. Obviously, it cannot be negative because probability cannot be negative. So mod of that. Okay. So it is then Pxy, only one solution. One is AZ plus BW, another is CZ. C means capital C plus dw divided by mod AD minus BC. Further, suppose it is given that x and y, they are jointly normal. Then our claim is z and w also are jointly normal. Why? Obviously, Pxy, this is given to be jointly normal. Okay. So it will have an exponential form, okay, where this will be squared and this will be squared. Okay. Of course, the corresponding variances and other things will come up, but the square term involving Az plus Bw and again a square term involving Cz and Dw will be present. And when you square them up, then you collect the terms with power z square, so you get one expression for that. Again you collect the terms involving w square, get another expression, and then there is a cross term involving the product zw with some coefficient. So that is, and the whole thing has to be a probability density. Okay. So that is the typical form of a Gaussian density function, where you have got an exponential form, it is joint density, there will be square term involving one term, square term involving another variable, and a product involving the two variables. Of course, these are with some coefficients, they will determine the new variance and new mean. Okay. So, obviously, it follows that under such linear transformation, if x and y are given to be jointly Gaussian in the beginning, then ZW also are jointly Gaussian. Okay. Obviously, what is what is the mean of Z? That is A times mean of x plus B times mean of y. What is the mean of W? C times mean of x plus D times mean of y. Similarly, you can find out the individual variances of ZW. You can find out the correlation, expected value of the product ZW. Just multiply the two. Okay, all these are possible. So, those will be appearing in the joint density expression, and we will see that it corresponds to our joint Gaussian function. Okay. So, now I come back to our previous example involving moments. Again back to joint moments. Suppose as before x and y are given, they are jointly normal, or you can say they are jointly Gaussian. Okay. It is given that mu x is equal to 10, mu y is equal to 0, sigma x, not sigma x square, but sigma x equal to 2, sigma y is equal to 1, and the correlation coefficient R x y is equal to 0.5. Okay. And you obtain two random variables z and y, z and w as a function of x and y. In fact, as just linear combinations of x and y, this is given that z is equal to x plus y, w is equal to x minus y. What we have to find out is the moments for z and w. Okay. Obviously, mean of z and mean of w very easy to find out. Then variances of z and w and the correlation coefficient involving z and w. This we have to find out. Okay. All right. So, what is mu z? That is E of z. There is nothing but E of x plus E of y. E of x is 10, E of y is 0, so this is 10. Okay. Similarly, again 10 obviously, because E of x which is 10 and E of y is 0, so 10 minus 0, 10. So, these two moments are done. Then what is sigma z square? We had already seen earlier that if x and y are added, the corresponding variance is what? That was sigma x square plus sigma y square plus twice r sigma x sigma y. Sigma x square is 4, sigma y square is 1, and twice r is rxy, so 2 into 0.5 into sigma x 2, sigma y 1. So 4 and 5 and then 2, so it is 7. Okay. Similarly, what is sigma w square? E of whole square of these. So, that is sigma x square plus sigma y square minus E of x y. What is E of x y? Sorry, what is sigma w square? Sigma w square is expected value of w minus its mean whole square. Okay, that is, you can say that sigma w square is expected value of w minus mu w square, right. Now, w minus mu w, w is x minus y, okay, and what is mu w? Mu w is mu x minus mu y. So, you can proceed like the way we proceeded in the case of z equal to x plus y. So, one term is you can write like this, x minus mu x minus y minus mu y whole square, right. Mu w is nothing but mu x minus mu y, w is nothing but x minus y. So, I have just substituted here, squared up. So, one term will be coming from the first term, which will give rise to sigma x square. Another will be coming from this term, square of this term expected. So, that will give rise to sigma y square. And there will be one more term minus twice expected value of the product of these two, which is the covariance between x and y. And what is covariance? Covariance is nothing but r x y sigma x sigma y. So, if you put them back here, what do you get? What is sigma x square? That is 4, sigma y square is 1, 4 plus 1, 5, minus twice 0.5, that is 1, sigma x is 2, this is 1. So, 2. So, 5 minus 2, which is 3. Okay. And lastly, we have to find out the correlation coefficient between z and w. Now, what is the correlation coefficient? That is covariance divided by respective variances. That is, I am taking the square on both sides. This was coming to be the square of covariance, right. So, E of z minus mu z times w minus mu w, you can expand it and you get this thing. Okay. Minus E z, that is mean of z, E of w divided by sigma z square sigma w square. What is E z w? This you have to find out. Okay, what is E z w? Okay, break it up, x square and minus y square. So, E of x square minus E of y square. Okay. What is E of x square? It is nothing but, we have seen, mu x square plus sigma x square. Similarly, mu y square plus sigma y square. Okay. What is mu x? 10. So, 100 plus 4. So, 104 minus mu y we have seen is, in fact, mu y is given to be 0, sigma y square is given to be 1. So, 104 minus 1, which is 103. So, you put those here, 103 minus E z, E w, E z we have already find out. Okay. E of z was 10, E w was 10, divided by sigma z square, and sigma w square, sigma z square is 7, sigma w square is 3. So, 103 minus 100, that is 3, 3 by 7 into 3. So, it is 1 by 7. That means, in short, we can say they are jointly Gaussian like this. N stands for normal, and normal is same as Gaussian. Firstly, the mean. So, the mean of x is, mean of z is 10, mean of w is 10. Then the variances, not variance, standard deviation. So, square root of the variance, positive square root 7 for sigma z, square root 3 for sigma w, and the correlation coefficient, which is 1 by square root 7. Square of correlation coefficient was 1 by 7. So, this is 1 by root 7. Okay. All right. Now, we go to the next topic, and that is we have already seen what is a characteristic function in the case of single variable. But now we have got two random variables x and y, and we have got their joint density function p of x comma y. So, obviously, we will have a Fourier transform with two frequencies, omega 1 and omega 2. So, we define the joint characteristic function as e to the power j omega 1 x plus omega 2 y dx dy. So, given p of x comma y, or you can equivalently see also that is nothing but expected value of e to the power j omega 1 x plus omega 2 y. Okay. So, given p x comma y, we can find out phi by this formula, and giving the characteristic function, we can find out p of x comma y by the inverse formula. That is again obtained by just by recalling the forward and backward Fourier transform relations. So, that is direct and indirect, okay, inverse, direct and inverse Fourier transform relations. Okay. That is, you can see that if you multiply both sides by 1 by 4 pi square, then this is nothing but inverse Fourier transform of p x comma y at omega 1 comma omega 2. See, there is a plus sign here, no minus sign, no minus sign. We recall in the one variable case, the inverse relation was 1 by 2 pi integral some function of say x e to the power j positive, it will be plus j omega x dx. Here we just have two variables x comma y. So, p x comma y e to the power this, okay, 1 by 4 pi square. So, this is again inverse Fourier transform of x comma y at omega 1 comma omega 2. So, p x comma y is nothing but direct Fourier transform of this quantity. Okay. That is p x comma y p x comma y is 1 by 4 pi square okay. So, this is the definition, and from the given phi omega 1 omega 2 we can also find out the marginal characteristic functions, that is just phi of omega 1 and phi of omega 2, phi of omega 1 being the characteristic function of x, okay, for the random variable x alone, and phi of omega 2 being the characteristic functions of the random variable y alone. Okay. And then we will see that when two variables are independent, statistically independent, then this joint characteristic function becomes just a product of the marginal characteristic functions, and vice versa. That is, if the joint characteristic functions is a product of two marginal characteristic functions, then x and y they are statistically independent. Okay. And then we will relate that to convolution and all that. So, that will be for the next class. So, that is all for today. Thank you very much. Okay. So, in the previous class, we ended with just a brief description of what is called joint characteristic functions. So, today we start from there. Maybe there will be a little repetition, but that will only be helpful. So, here we are given two random variables, say x and y. Jointly random. Then we have already seen what is a characteristic functions in the case of a single random variable. So, here we will be simply extending that to the case of two variables. So, here the joint characteristic functions earlier was a function of only one frequency omega. Now, since there are two random variables x and y involved, there will be two frequency variables omega 1 and omega 2, and it will be defined like this. Omega 1 x plus omega 2 y dx dy. You can also see that this is nothing but the expected value of this exponential. After all, this is a function of x and y. If I want to find out its expected value, I simply multiply it by the joint probability density, integrate it from minus infinity to infinity, both with x and y. So, essentially joint characteristic functions phi omega 1 omega 2 is nothing but the expected value of e to the power j omega 1 x plus omega 2 y. Then we can also see that I can write this, if this is given, I can write this as this, they multiply left hand side by 1 by 4 pi square, this also 1 by 4 pi square. Then you can easily see that the right hand side is nothing but inverse Fourier transform of this function p x comma y. Okay, inverse Fourier transform of this function of two variables. So, you have got a plus sign here e to the power plus j. So, it is not minus because it is inverse Fourier transform, it is power plus j omega 1 x plus omega 2 y. So, there are two frequency variables, integral as usual is from minus infinity to infinity. In the case of inverse Fourier transform involving only one variable, we have 1 by 2 pi, but since there are two variables, it becomes 1 by 4 pi square, right. If that be the case, then we know that p x comma y also can be viewed as the direct Fourier transform of this quantity on the left, 1 by 4 pi square of 1 by 4 pi square times phi omega 1 omega 2. So, that means there is an inverse formula that is given the characteristic functions, joint characteristic function now the minus sign will come, it is power minus j omega 1 x plus omega 2 y, but the integral will be with respect to omega 1 and omega 2. Okay. Certain things you can see now. Also, one more definition. Let me remove this 1 by 4 pi square now. This was just for explanation purpose. Along with phi omega and omega 2, there is another definition which also comes out to be useful sometimes. Actually, often phi omega and omega 2 is seen to be, in practical cases, seen to be an exponential function. So, instead of dealing with phi as such, it's sometimes better to take logarithm of this, and then twice when k is 1, obviously this 2 1 will be 1 will become 2, okay, because factorial 2 divided by factorial into factorial 1. So, twice e, and now x to the power 1, y to the power 1, s 1 to the power 1, s 2 to the power 1. So, m 1 1, s 1, s 2, so on and so forth. We stop here today, and from this we will derive some new results and take up some examples, okay, in the next class. Thank you very much.